Math in motion, the shapes that build our universe. Imagine you are an engineer designing the next Formula One race car or a mission specialist calculating fuel for a Mars rover. The math you are learning now, calculating the volume of cylinders, cones, and spheres, is the actual code used to build these machines. In the STEM world, these aren't just shapes on a paper, they are the fundamental building blocks of power, speed, and efficiency. The cylinder, the heart of horsepower. Picture a high-performance car engine in slow motion. Inside, you see metal pistons pumping furiously up and down inside smooth metal tubes. These tubes are cylinders. The displacement of an engine, like a 2.5-liter engine, is actually the total volume of these cylinders. Engineers must calculate this volume, $V equals backslash pi r squared h dollar, precisely to determine how much fuel and air can fit inside. A tiny error in this calculation means the engine won't generate the combustion force needed to win the race. Visualizing this animation helps you see that volume equals power potential. The cone cutting through the atmosphere now. Look up at a SpaceX rocket sitting on the launch pad. The very top of the rocket, the nose cone, is a perfect geometric cone. Why? 'Cause volume and aerodynamics go hand in hand. Aerospace engineers calculate the volume of the nose cone, $V equals backslash frac 3 backslash pi r squared h dollar, to balance the payload capacity, how much satellite equipment fits inside, against the need to slice through the atmosphere with minimal drag. If the cone is too wide, the drag is too high, too narrow, and the expensive satellite won't fit. The sphere storing the impossible. Finally, imagine a pressurized fuel tank on a spacecraft or a massive natural gas storage container. These are often spheres. In engineering, a sphere is the perfect shape because it holds the maximum volume for the minimum amount of surface area, $V equals backslash frac 3 backslash pi r caret $3. This means you can store more fuel with less metal material, making the ship lighter and cheaper to launch. Even at the microscopic level, bioengineers study the volume of spherical cells to understand how medicine disperses in the human body. Why it matters when you solve for $V dollar, you aren't just finding a number. You are calculating the capacity of a lung, the fuel range of a jet, or the habitability of a planet. You are learning the language of how things fit, move, and function in the physical world.